We're going to pick up here chapter 14 still. We got into titrations last time. Specifically, we got into this titration of a strong acid and a strong base titration. Again, as we were talking about in this situation, in the burette there, we have our strong base, like our sodium hydroxide. In the beaker, glass, whatever it may be, R square in this case, we have the HCl. And we are adding our sodium hydroxide to our HCl. And we talked about this titration curve that we see down here. And this is typically what a titration curve sort of looks like. It's sometimes referred to sort of as an S shape. And as we talked about, and as we'll continue to talk about today, there really is sort of 4 distinct parts to a titration curve. There is really the first point here, which is before you start the titration. And that's really, in this particular example, before you add any sodium hydroxide to it, you basically just have a strong acid in the beaker. So as we talked about, pretty much to get the pH of your initial solution, it really is just a strong acid type problem. And because it's strong acid, that pretty much means you should have the H+ concentration, and you really could go directly into the pH equation at that point. And that'll give you sort of the opening pH there of your solution to start your titration. The next sort of important point on the titration curve that we talked about is pretty much from the very first drop there to right before the equivalence point. And that is sort of our second point in the titration. This is a point where you obviously are starting to add sodium hydroxide as you're working your way to the equivalence point. And because of that, we will get a chemical reaction that will occur, and it is this reaction right here in this particular example. It is the sodium hydroxide plus the HCl making water and sodium chloride. Because we are adding volume, and as we've been talking about, whenever we add volume to another volume, the molarity of those solutions change, but the moles basically stay the same. So it does require in this sort of region for you to do an ice table. That ice table does need to be done in moles. And really at this point, you will have plenty of your strong acid to handle whatever base comes in from the strong base. And the purpose of this ice table is really to figure out what is your new concentration of your strong acids that you have left over in the beaker as it changes when you add some of the sodium hydroxide. So we would want to do this ice table in moles. That means we also will know what the change is. It should be the smaller number, right? Because that's like the limiting reagent. And we do want to, after the first ice table, convert those moles back into molarity using the total volume. And that would be obviously the volume of the acid you started with and how much base you added to it, converted to liters. At that point, you really will have a couple things left over. You have a salt that's a neutral salt. That's this guy right here, sodium chloride. And you also have some HCl left over, which is obviously your strong acid. Once you get the correct concentration of your strong acid at that point, you could go into the pH equation and get the pH to determine it. The third important part of a titration curve really is the equivalence point. And remember, the equivalence point is that point where the moles of the acid in a titration like this will equal the moles of the base. So that is the exact point where both of those things will equal each other. And what that really means is if you did an ice table, these moles here should be the same, and they will essentially be gone when it's all said and done. That will leave you in this type of titration really just a salt that's left over when you do that ice table. And because that salt came from both a strong acid and a strong base, that means it's going to be relatively weak, and it will be a neutral salt. So the pH in this type of titration at the equivalence point should really be a pH of 7, which is what we see here in the table, because really you will always be left with, in this type of titration, a salt that will not go through hydrolysis that's considered basically a neutral salt. The fourth part of the titration curve, which is most important here, is basically after you reach that equivalence point. So in a traditional titration, a lot of times we do stop at the equivalence point, but when we're making something like a titration curve here, we actually go past the equivalence point. And to go past the equivalence point, we are still going to get that reaction that's going to happen. You will need to do an ice table here. Once again, this ice table will need to be done in moles because you're adding volume. In this case, though, because we have passed the equivalence point, the moles of the base that we're adding should be actually more than the moles of the acid we started with, because we're basically past that equivalence point. That tells us that there's actually a switch that occurs, and that means that in this case, the acid would really be the limiting reagent and the base would be your excess reagent. So the purpose of this ice table past the equivalence point is to really just to, if you think about the titration past the equivalence point, you're pretty much in this case just dumping base in there. So the purpose of the ice table is to figure out what is the concentration of the strong base that you have in there. That's going to allow you to get to the OH minus concentration, to the POH, and then to the pH at that point. Would allow you to calculate the pH at that instance. So there's sort of 4 distinct points along any titration curve like this, and it's important to understand where you are in the titration curve. It can obviously help you with the type of calculation that you should be doing, depending on where you're at. We also talked about a couple of important things that sometimes happens in titration problems, which is they sometimes will not tell you the volume to reach the equivalence point. So you sometimes do need to figure it out. Again, if it's a 1-to-1 relationship between the acid and the base, you could use M1V1 equals M2V2, where the first guys are the acids, the second guys are the base, and you can just solve for it. If it's not a 1-to-1 relationship, you really do have to do a stoichiometry problem. The other thing that we talked about is because it is the equivalence point, you will know the moles of the base that you need, and you know the molarity of the base, so you can use the moles and the molarity to figure out the volume that you need. The reason, again, it's important to figure out at some point during the titration, you know, how much volume to reach the equivalence point is because maybe not in this type of titration, but in future titrations, you may need the molarity. So you need the proper total volume at that point to convert it back to molarity. Any questions on that? Yeah. It will not always equal 7. So what we're talking about here is specific to this type of titration when we're using really a strong acid and a strong base combination. So it will change, and we're going to talk about next basically what happens when we do a weak acid and a strong base, and also a sort of strong acid and a weak base. So there are some differences in the different type of titrations, but specifically the one we talked about last time is this one, and this is sort of how you handle the pH anywhere along that curve. Other questions? So why don't we try one here? Let's say we did this titration here. We want to know what is the pH after we add in this titration. We'll go with why not 23 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar HCl. All right, so calculate up the pH in this case. Again, it's the same titration we've just been talking about, so we're adding the sodium hydroxide to the acid. Okay, let's take a look and see. So obviously we're doing a titration here, and we've obviously added some sodium hydroxide at this point. So we do want our reaction. So our reaction here, HCl plus some sodium hydroxide, going to give us, right, it's a little salt and water. So we'll have some H2O and some sodium chloride in this case. Right? All right, now since this is definitely adding volume here, we need to do this ice table in moles. So we want to convert everybody into moles. So we will convert our milliliters into liters. And that gives us 0.023 liters times our molarity of 0.1 moles per liter. gets us something like 0.00230 moles of sodium hydroxide. We'll do the same thing here for our HCl, converting our milliliters into liters using our molarity, 0.1 moles per liter. Gives us 0.0025 moles of HCl. Any questions on that so far? All right, so initially here, we are going to take our moles of HCl, 0.00250, and take our moles of sodium hydroxide, 0.0023, and nothing here, right? The first question is, am I before, at, or after the equivalence point in this case? We can know by looking at our table, right? This is what we started with, right? In terms of our HCl, this is what we are adding. The moles of what we're adding, is it less than, equal to, or greater than what we started with? Is less than, right? And we know if we are at the equivalence point, those moles should be equal to each other. And since we are less than for our base, we haven't quite reached the equivalence point. So we know by looking at our numbers here, we are before the equivalence point because we have less of what we're adding than what we started with. Yeah. Any questions on that? That's also important because that will also tell us that at this point in the titration, the limiting reagent should be the sodium hydroxide. So the change part here is going to be minus 0.0023 minus 0.0023. Remember, you cannot have a negative number, so just keep that in the back of your mind. All right. That means when we reach equilibrium here, we will end up with 0.0002 moles, 0.0023 moles. At this point, we do want to convert back into molarity. It's really good practice here. So our total volume at this point is, we started with 25 milliliters. We added 23 milliliters. That's like a 48 milliliters. So we're going to divide each of these by 0.048 liters here, technically would convert us back into molarity. So taking that guy divided by 0.048, going to get us 0.00417, we'll call it. And if we do this guy here, .0479 molar. At this point, if you're not sure what's going on, once again, you can use your ice table to help you figure out maybe what the next move should be. At this point, we see this guy and this guy left over. First off, or is that a buffer? That is not a buffer because HCl is a strong acid, right? You can't have a buffer of strong acid. So again, we would not want to use our Henderson-Hasselbalch equation here because that is not what we should do. We've talked about this salt. This salt comes from a strong acid and strong base, which means it's neutral, which means, frankly, don't even really care about it. It's not going to affect the pH. That means really the only thing we have left is our HCl, which is a strong acid, which means that would be our H+ concentration in this case because it comes from HCl. And that means we could just go into our pH equation. And we'll do minus the log of 0.00417. We used a rounded number there, minus the log 0.00417 looks like. Looks like a pH of 2.38 at this point in the titration. Let's see how we did. That's 22, that's 24, 2.38 is in between those two, so that's good. Not too bad. question on that one. So it's important to make sure that you obviously calculate the pH correctly. And as I mentioned before, very common, people get two numbers and go, I want to use the Henderson-Oswald equation. Question? The NaCl is a salt that comes from basically these two things, right? Our strong acid and strong base, which means, as we talked about, when we talked about salts, if we just look at the sodium chloride by itself, it basically is a sodium ion and a chloride ion. The sodium ions group 1 or 2, which basically means it comes from a strong base, which means it's a weak acid and will not go through hydrolysis and is considered neutral. So we don't have to worry about it. The Cl minus comes from HCl, which is a strong acid. Also means that it's a relatively weak base and will not go through hydrolysis, which also means it's a neutral. So we don't even have to worry about sodium chloride in this case, because it should be a pH of 7, which means it won't have an effect on the pH of this solution at this point. You actually don't need to put numbers. I did in this case because people often do. So just to point out the fact that if you do end up with two numbers, you really should analyze what you have going on in that table and make sure that you don't maybe go down the wrong path and think of buffer or something like this. Yeah. It will always be a neutral salt in this type of titration because it's a strong acid and strong base, which means the salt has to come from both of those things. And that means that the salt has to be neutral basically in that case, because it does come from both a strong acid and strong base. So specifically to this type of titration, it will always be a neutral salt. Yeah. And that's why when we get to the equivalence point, like we talked about in this type of titration, it will always be a pH of 7, because whatever that salt may be, sodium chloride, whatever other salt it may be, it will always have come from a strong acid and strong base, which means it will be neutral as well. And there'll be no hydrolysis happening. Other questions? Okay. All right, so that is our strong acid, strong base titration. We're now going to talk about the next type of titration, which is a weak acid and a strong base titration. So a weak acid and strong base titration, we have kind of a very similar setup. So we'll do our acetic acid and sodium hydroxide. So in this case, we're going to set up with our sodium hydroxide up here in the burette. In the beaker or the flask will be our weak acid, which is our acetic acid in this particular case. So once again, we do see a very similar sort of titration curve that we saw with the strong acid and strong base. And we're going to talk about the same four sort of parts again to this titration curve. Once again, our first part here will be before we start the titration. Our second part will be when we start the titration to our equivalence point. The third part will be the equivalence point itself. And much like the last one, our fourth part here will be after we come past the equivalence point. So this type of titration is a little different in the sense of how we need to solve for the pH because of pretty much what we are dealing with. So let us take a look here first off at part 1 of this titration and sort of see what happens there. So at the very beginning here, before we add any sodium hydroxide, the only thing we have in our beaker or our flask is, like in this example, acetic acid. We basically have a weak acid. And if we wanted to find the pH of a weak acid, we should do what? We should do a ice table. So this is really just like a Ka type of problem that we did earlier. Because of this, we would take, in this example, the acetic acid, and we would let it dissociate into H+ and acetate. This would be an ice table where we could use molarity because we have not added any sodium hydroxide yet. So we don't have to worry about using moles in this table. And because we're using molarity here, we will use our X's in this table. So we'll do our normal sort of X move here. We'll take our initial molarity minus X, X, and X. Like normal, we would go into our Ka expression, which in this case would be H plus our acetate divided by our acetic acid. And that would equal our Ka value, which by the way is 1.8 times 10 to minus 5 in this case. We would obviously solve for X, which may involve an assumption, non-assumption, whatever works like normal. When we do solve for X in this case, it will equal the H plus concentration here from our table. So that will equal our H plus concentration. And now that we have that, we could go into our pH. So you can see that this one is quite different than the last titration, where we started with a strong acid and all we had to do was go directly into the pH equation. In this case, because we're starting with a weak acid, it does require us again to do basically a Ka type problem. So you kind of start out with a Ka type of problem. Also, because this is a weak acid, if you look at the titration curves between the strong acid and strong base and this particular one, you'll also see that we would probably start a little bit higher in terms of our starting pH. It's still acidic, but a little bit higher than, say, a strong acid is typically where we would start. Any questions on before we add anything to it? All right. Now that we got our initial pH in this titration, the next thing we're going to do is actually start the titration. So we're going to be before the equivalence point. So what we want to look at here is what happens, really from the first drop of sodium hydroxide up until the equivalence point. So really in this second region here. So let's talk about what happens there. When we get to the second part here, our area of the titration curve, which is really before the equivalence point, we obviously have added some sodium hydroxide. So this again is going to require us to do an ice table. And we will do our ice table in this case with our weak acid, plus our sodium hydroxide, going to do a little double displacement type of deal here, going to make a little sodium acetate and some water. Now, when I do this ice table here, because I'm adding sodium hydroxide, should this ice table be done in molarity or moles? This should be done in moles. Again, we're adding volume. So that's what we would want to do here. So we are starting with acetic acid. We are adding sodium hydroxide. So once again, like we did on the first titration curve here, I'm just making up the number. I'm going to say we start with 4 moles of acetic acid. So I just made that up in my head. Because I am before the equivalence point, should the moles of my sodium hydroxide be less than, equal to, or more than that number? Should be less than, right? Because we haven't hit the equivalence point. Once again, making the number up here is going to be 2 moles in this case, and we'll have 0. Since we are not at the equivalence point, what we know is our sodium hydroxide in this case will be like the limiting reagent. So it should be the change that should occur here, -2, -2, and perhaps a +2 on this side. That gets us to the equivalence or equilibrium of 2 moles of this guy, 0 this guy, and 2 moles of that guy. Any questions on that so far? Just like normal, we do want to convert now back into molarity. And again, we would use our total volume. So again, the amount of acid we started with, the amount of base that we added together, we would most likely need to convert it into liters and divide each of these guys by liters, which will convert us back into molarity. And again, this is really our total volume at this point, which should be the acid plus the base, or the milliliters of the acid plus base. Now that we have this ice table done, we could look at the ice table once again to help us understand what should be happening at this point. We have some acetic acid left over. We have some sodium acetate left over. First question is, are those two things related to each other? They are, yes. That is a weak acid and its conjugate base, or the salt of its conjugate base. That is also known as what type of solution? That is a buffer. So we basically just created a buffer here, which is part 3 of the experiment coming up on Thursday, is doing this type of idea here. So as we talked about before here, you cannot have a buffer that's made up of a strong acid or strong base, but you could use, for example, like we did here, a strong base and a weak acid and react them. And the buffer actually comes at the end of that reaction. So the strong base is no longer there, but the results of that reaction creates a buffer in this particular case. But because it is a buffer and we're really interested here in the pH, that means we really have 2 ways that we could solve for it at this point. I probably think the Henderson-Hasselbalch might be the best move at this point. We could go into our Henderson-Hasselbalch equation, making sure that we take the pKa value from the weak acid. Your other option is you can do a second ice table at this point. And the second ice table, if you chose to do that without using Henderson-Hasselbalch, would be really just the weak acid. And if I chose to do the ice table instead of the Henderson-Hasselbalch, the really important part of this ice table is you should have a molarity here. This should be 0. And you need to make sure you have a molarity here. So again, if you do not have that one there, if you did the ice table, you are not doing a buffer, you're doing a weak acid. So if you choose to do the ice table, it should come out the exact same as the Henderson-Hasselbalch, bless you. But you got to make sure that you have that second concentration on the other side, which is very commonly missed by people when they go ice table rather than Henderson-Hasselbalch. Yeah. It would come from the equilibrium line of your first. So in this example here, this guy would end up here, and this guy would end up here. And that's important that you put both of those back in there, like I just said. Again, otherwise you're really not doing a buffer problem at that point. Yeah. Other questions? And the rest of the table obviously would be X's, and you would solve for X, you would get the H+ concentration, and then obviously into the pH at that point. Again, I would say probably if you can recognize as a buffer, this is probably the way to go. Probably a lot less room for error, but you definitely could still do the ice table if you wanted to. Any questions on that? So as you can see, this titration, a lot different than the previous titration before the equivalence point, where you still have just a strong acid left over. Here, you will always end up with a buffer in this range, which is why we gotta have a pH not climbing a lot. But what's happening towards the end here, where we start to see it climb, is you're blowing through your buffer at this point, right? Because you're constantly adding base. And at some point, you're going to blow through the buffer part, and you're going to see that jump in the pH. So that's basically a buffer through that region where you're not really following instructions. You're just adding base, going crazy. Because remember, when you add the base, you will use up the acid part, right? Make the base part. And at some point, you will blow through the acid part of the buffer, no longer being able to behave as a buffer. And that's why we see that really big jump to the equivalence point. And obviously, as we talked about as well, once you continue to add that base, you're going to see another jump past the equivalence point as well, because you're adding it in there. Any questions on that? So second part here, no matter which combination of a weak acid, strong base you end up with, you should always end up with a buffer. And again, this is why it's good to know where you are in the titration, because you should know, hey, I should be probably doing a buffer problem at some point. And again, it's good to kind of know what you should be doing before you just kind of jump in to try to do it. Any questions on that? All right, then. Question? You good? Yeah. Always in this part of the titration curve. So before the equivalence point, you should really always end up with a buffer, a good buffer, bad buffer, but some type of buffer type situation will happen. All right, so let's talk about here what happens when we do reach the equivalence point, which is number 3 up there. So let's take a look at that. So at number 3, we are going to be at the equivalence point. And when we're at the equivalence point, we obviously will still have our same reaction. So in this case, we'll have our acetic acid plus our sodium hydroxide, making some water and a little sodium acetate in this case. However you want to write it. So once again, we're still adding volume at this point. So we do need to do this ice table in moles. And I'm going to use my made up number of 4 moles. This is obviously what we're starting with. And this is what we're adding. So now that we have reached the actual equivalence point in this titration, the moles of my sodium hydroxide should be less than, equal to, or greater than. Should be equal to, right? That's basically, again, the definition of the equivalence point. So I should have obviously 4 moles here and a 0 going on there. At this point, you really can't choose wrong, I hope, because it's the same number. So you should choose that number would be good. So that's going to be -4, -4 in this case, and +4 in this case. That means when we reach the equivalence point or equilibrium here, we have none of the acetic acid. We have none of the sodium hydroxide, which we would expect because we're at the equivalence point. And we have 4 moles here of this guy. And like normal, we will now convert it back into molarity using our total volume. So we're going to again add up the amount of acid we started with plus the amount of base we added, convert it to liters, and convert this guy back into molarity. Any questions on that ice table? Once again, when we're at the equivalence point, because we do know that we should have the same number of moles, once again, if we needed to figure out the volume, you most likely will have the molarity of the base. You'll now have the moles of the base. So once again, molarity is moles per liter. You could solve for liters at that point and figure out how much sodium hydroxide you would need to add to get there. Now that we look at our ice table at this point, we can figure out maybe what's going to happen. I have pretty much this guy left over. That is sodium acetate. What is sodium acetate? Sodium acetate is a salt, right? That will basically break apart, as you mentioned there, into 2 ions, right? It's going to break apart into a sodium ion and an acetate ion. We clearly know from our conversations before, sodium should be a neutral salt, right? So we don't have to worry about it. And what about acetate? Do we have to worry about it? We do, because as was mentioned, the acetate comes from this guy, which means this is a weak acid, which means this is going to be really the conjugate base. And because it comes from a weak acid, it will go through hydrolysis and it's going to react with water that's hanging out there. So what happens in this point of the titration, unfortunately, you can't just put pH of 7. That's unfortunate here. We will actually have a hydrolysis problem that will occur. So we will need to do a second ice table, and the second ice table is a hydrolysis problem, and that is our salt, which we know comes from a weak acid, which means it's going to act as a base, right? When it reacts with water, and that's good to know because it means it's a base, it will accept the H plus from water, right? And when it accepts the H plus from water, we are going to make acetic acid, which is always where it comes from is what you make. And we will produce hydroxide, which means without even completing this calculation, we should know at the equivalence point here, should the solution be acidic, basic, or neutral? Should be basic because we are generating hydroxide here. So we should have a basic solution. By the way, we do need to do a calculation, which means I should use what type of K value in this case? Should use a KB. You most likely will not have a KB value given to you in this problem. You will have the Ka value for the acid. So that is where we use our Ka times Kb equals Kw to convert it. So you probably will need to use a little Ka, Kb equals Kw type of action there to make sure that you do get the Kb. So this ice table will be done in molarity, which is why it's important back here to convert it back to molarity. And obviously, kind of like what we were just talking about in the previous one, it is this concentration here that should end up right there. Yeah, so you're going to take your initial concentration there from the equilibrium line that should end up there. The rest of this will be zeros and x's. This is going to go into, as we just talked about, the Kb value, not the Ka. And once again, at this point, you would use the proper Kb value. You would solve for x. It's also really important to remember when I solve for x in this case, what does it equal? It equals the hydroxide concentration, not the H plus. So that means that that's going to equal the hydroxide, which means you got to first go POH and then to the pH at this point. So a little bit more work here at the equivalence point in this type of titration than we had with the strong acid and strong base, where we just wrote 7 at the end of it. And that's really because in this type of titration, regardless of the weak acid and strong base that you use, at the equivalence point, you will always end up with a salt that basically came from a weak acid. And because it came from a weak acid, it will always go through hydrolysis. It will always create hydroxide, and it should always be basic at the equivalence point in this type of titration. Question on that there. And that is what we see if we do look at the curve here at the equivalence point. That looks basic to me right there. And that is what we would expect to happen here rather than our pH of 7 in a strong acid, strong base. By the way, that's also how you could tell, perhaps, that you're doing a weak acid versus a strong acid in a titration with a strong base. If you end up with an equivalence point near 7, it's probably a strong acid. If you end up with an equivalence point that's basic, it's probably a weak acid. This is also why they yelled at you when you did your titration with phenolphthalein, as we talked about, I think, the other day, to go for the lightest color pink, because your equivalence point should be in the 8-ish range, which is right where phenolphthalein starts to develop a color. And that's why you try to get it to the lightest color pink that you can to stop, hopefully, at that area. Any questions on the equivalence point here? Yeah. It has to go through hydrolysis because no matter what combination of weak acid and strong base that you have at that point, this salt, for example, that is going to be generated will have always come from a weak acid, which means the salt will go through hydrolysis and it will act as a base, which means it will always accept the H plus from the water. And by accepting the H plus from water, it will always generate the hydroxide. And that's why it will always be basic at this point, no matter what. Again, for this type of titration, weak acid, strong base. Other questions? So let's talk about the fourth part of this fun titration curve here. And we are going to go past the equivalence point and see what happens. All right, so past the equivalence point. We still have our reaction, which is acetic acid in this example, our weak acid, and our sodium hydroxide, which is our strong base, going to give us the same results here. A little bit of water and some sodium acetate here. And once again here, because we are obviously still adding sodium hydroxide at this point, we want to do this in moles. And I'm going to use my starting amount here. This is what we're adding. And once again, I'm going to use my made up number of 4 moles. And now you're going to tell me that the moles of sodium hydroxide should be less than, equal to, or greater than at this point. should be greater than, because we are now past the equivalence point. So again, we'll make up a number of 6 moles, and we'll do 0 here. Because we are pretty much at this point just dropping in sodium hydroxide, the sodium hydroxide at this point does become, again, like the excess reagent. We do not have enough of the acid there, or the acetic acid, to handle that. So the change part here is going to be our acid in this case. Remember, just logically speaking, you cannot have a negative number, so always take the smaller number. This will get us now at this point in the titration, none of our acetic acid. We'll have a couple of moles of this guy. We'll also have 4 moles of this guy. And like normal here, now that we have got our moles of everybody, we're going to use our volume here, our total volume, to convert it back into molarity at this point. All right, so looking at our table here, we have some sodium acetate left over. We got a little sodium hydroxide left over. First off, are those things related to each other like a buffer? They are not a buffer, right? They're not really even related to each other. We got sodium hydroxide and we got sodium acetate. So we got to think about, will these things affect the pH? So clearly from our conversation at the equivalence point, we do know that this guy will go through hydrolysis. It will act as a base, right, and accept that H+. We also know that sodium hydroxide is a strong base. Between the two of them, which one would you expect to be probably the major contributor to pH at this point? The sodium hydroxide, because it's a strong base, which means, frankly, in order for it to affect the pH, it just has to go for a swim. It's going to go for a swim, break apart. You just produce hydroxide. The acetate's got to go find some water, do a little bit of a reaction. It's a reversible reaction, so it's not going to generate as much hydroxide than just simply dumping in the sodium hydroxide from your burette, and it's just going to make that hydroxide. So even though the acetate is contributing a little bit, it is nowhere near the amount of OH minus going to be contributed by the sodium hydroxide in this case. So at this point in the titration, we actually ignore the contribution of the salt, and we really just focus in on our sodium hydroxide as the major source of hydroxide in this part of the titration, which is good because sodium hydroxide is a strong base, which means essentially this number in most cases will be your hydroxide concentration. And now that you have the hydroxide concentration, you can get the POH, and then you could get the pH, which probably should be basic at this point, because frankly, you're just dumping in base at this point, hydroxide ions. So past the equivalence point, you are required to do an ice table. The purpose of the ice table is really to figure out the concentration of the strong base you have left over. And then you basically get the POH into the pH. Any questions on that? So always at this point in the titration, you pretty much can ignore the contribution of the salt, as sodium hydroxide is a much stronger base than acetate in this case. Any questions on that there? No, this would be it. You do need to do at least one ice table, which would be something like this. And at the result of that ice table, you basically have the concentration of your strong base, which means you could go right into the POH and then into the pH at that point. Other questions? So a lot more happening in this type of titration than obviously we saw in the previous one. You got to do a Ka problem here, right? Which is good because we know how to do that. You pretty much need to do an ice table and a buffer problem there. You need to do a hydrolysis problem there. And you need to do an ice table to figure out that, which is a strong base type problem. The good news on all these calculations is it's all calculations that we've done before. The problem that people have is like, what should I be doing where, right? So if you understand where you are in the titration curve, you should know like, hey, I'm before the equivalence point. I should be doing a buffer. I'm at the equivalence point. I should be doing a hydrolysis problem. So if you kind of know where you are in the titration before you kind of start the calculation part of the problem, it should help you make sure that you are doing sort of the right calculation. You know, it's like the directions, right? We could get in the car and just drive around and find the place, which, you know, we do. But sometimes it's good to know where you're going before you get in the car, right? It makes it a little bit easier of a trip, right? And that's what you want to kind of do in this case. Yeah. They will not. So the problems will just flat out tell you, hey, kind of like the last one we just did, you know, you added this many milliliters of the base to this acid, you know, what is the pH? So that's why it's important to how we've been doing, like, all right, this is the moles we started with, this is the moles we're adding. Are we less than, equal to, or greater than? That's how you could really use your ice table to figure out where you are in the titration, by figuring out, you know, how many moles of each one that you have. The other way you could do it, if you do know the volume of each, and this is a one-to-one relationship, you know, if you have less volume of the base and the acid, that also will work if it's a one-to-one relationship. But really, the safest way to do it is to start your ice table, look at the moles of each of the acid and the base, and try to determine that, you know, okay, equal means equivalence point. What we're adding is less than, so I'm definitely before, or what I'm adding is more than, I'm after, and you'll probably never go wrong, hopefully, in that case. Yeah. Yeah. Is it possible for the POH to be negative? The answer is yes, but not in most cases. So in most cases, both the POH and the pH should be positive numbers. Yeah, these are just made up numbers. In most cases, you won't have that. It is possible, for example, if you have a really concentrated, for example, acid or base, you can get a pH that's like a negative. And but most of the time in labs, we don't really use really high concentrations and stuff. So we use more dilute solutions, which should keep you on the pH scale of a positive number. They're sometimes referred to as super acids that can have kind of a negative pH, but you probably won't come across it too much. Yeah. But in this case, I was just obviously making up numbers, and we didn't really know the volume either, which would have probably brought down our molarity at the end. Other questions? All right, so why don't we try one here? Why don't we try, yeah, why don't we try one? Why not? Let's do this titration here. What is the pH? After we add, we'll do 23.5 milliliters. Why not? Of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar acetic acid. Ka value for acetic acid, 1.8 times 10 to the minus 5. All right, give it a go, see what you come up with. I'll do it as well. Okay, let's take a look and see. So obviously we're going to start with our equation here. So our acetic acid and our sodium hydroxide, as we are obviously in the titration. Going to make a little sodium acetate and some water. Once again, since we are obviously doing the titration here, we want to do this ice table in moles. So we will take our moles of our acetic acid, which would be 0.025 liters times 0.1, and get an error. Try that again. There we go. And that will give us 0.0025 moles. We're going to multiply the sodium hydroxide volume converted to liters. So divide by 1,000 or move the decimal place 3 places there. So 0.0235 times 0.1 gives us 0.00235 moles, and 0 this guy. Once again here, this is what we are starting with. This is what we are adding. Am I before, after, or at the equivalence point? I am before the equivalence point in this case, as I have less moles of what I'm adding to moles of what I am starting with. That tells me that the change should be the base in this case. So the change will be minus 0.00235, 0.00235, and plus 0.00235 moles. That means that when we do reach equivalence here, we got 0.00250 minus 0.00235. That gets us 0.00015 moles. 0 this guy and 0.00235 moles of this guy. Any questions on the ice table at this point? We now want to definitely convert these back to molarity. So we want some total volume at this point. So total volume is, we started with 25 milliliters of the acid. We added 23.5 milliliters of the base. That's like a 48.5 milliliters. So we're going to divide each of these by 0.0485 liters, which is that converted to milliliters converted to liters. That is going to get us 0.000150 divided by 0.0485. Gives me 0.00309 molar and 0.00235 divided by 0.0485. 0.0485 molar. Any questions on that there? At this point, if you're not sure what should happen, but you really should know because you know this, we have this guy left over, sodium acetate, and we have acetic acid left over. Those two things are a buffer, which is what we would expect to be happening in this type of titration before the equivalence point. That should focus you into, I know what I should do next, which is probably use the Henderson-Hasselbalch equation in this case. The pKa value would be minus the log of 1.8 times 10 to the minus 5. That's a 474. And that means that the pH here would equal the pKa plus the log of the base over the acid. Gets us 4.74 plus the log. The base is which one? The sodium acetate, because once again, this is acetic acid, right? So that would be the acid. So we want to make sure we get the right one up on top. 0.04. What's that number? 85, I think it is. 85 divided by 0.0309. All right, here we go. 0.0485 divided by 0.00309. A little log action of it. We'll add a 474 to it. We'll do like a 594 maybe as our pH at this point. Question on that there? Yeah. No, it's fine. Yeah. You mean when you did like the 3.09 times 10 to the minus 3? Is that what you're asking? No, don't matter. No, it's the same number. It's fine. Yeah. Other questions? Yeah, we'll see how we did. Hopefully we're between those 2 points. 5.9 is right between those 2 points, so that's good. At least we don't screw that one up. That's good. All right, question on this type of titration. I see a little bit different than the first type of titration we talked about. A little bit more going on. Obviously, on this one as well, you could have finished up with a second ice table instead of the Henderson-Hasselbalch if you wanted to. Should get you pretty much the same answer. All right, one more titration curve to talk about, which is a little bit different of a titration, and this is going to be a titration of a strong acid with a weak base. So the setup here is a little bit different. In this case, it is actually the acid up in the burette, and the base, in this case, an NH3, is on the bottom here. So we're actually adding acid to our base, which is why our titration curve looks upside down, because we're starting with a base, which is higher pH, and we're adding acid, which means it's going to lower it. It's still sort of that S curve upside down. And just like the other titration curves, they're still the same 4 parts that we want to be concerned with at the very beginning. When we add our drop to the equivalence point, at the equivalence point, and once again, past the equivalence point is our same 4 sort of areas on this titration curve. So let's look at each of these just like we did the other ones and sort of see what's going on at each of these steps and see how different it is or it is not. So let's start with the very first part here, which is before we add acid. So basically before the titration begins. In this case, what we have in the actual beaker or flask is NH3, which is a weak base. And in this case, if I wanted to figure out the pH of a weak base, I need to do a KB type problem like we've done before. So this will require an ice table where, remember, since it is a base, you probably do want to include water here. And because it's a base, it's going to accept the H plus, and you will get NH4 plus. You could either keep them together or break it apart into hydroxide here. And this would be an ice table done with molarity, as we have not added any acid in this case, so we're not mixing volumes. And these obviously would be some zeros, some minus x's, plus x's. Initial minus x, x, and x. This obviously, because it is a base, would go into our KB value. And like a normal ice table that we've done previously here, we're going to solve for x. And once again, in this case, we can see from the ice table that x does equal the hydroxide concentration, which means that we can get, again, not the pH here, but we got to go POH first and then to the pH. So again, it's kind of very similar to the one we just talked about, except that in the one that we just talked about, you had a weak acid to begin with. So you do a weak acid problem. Here you have a weak base, so you have to do a weak base problem. But very similar to the last titration curve. This titration curve is actually very, very similar to the last one, except that we're kind of going opposite in terms of the pH. We're starting high, going low. The other one, we're starting low and going high in terms of the pH. Any questions on that part of it there? All right, so then let's talk about what happens again here once we start adding acid in this case, all the way to the equivalence point. So that kind of second part. So the second part, which is before the equivalence point, we will get a reaction in this case of our weak base plus our strong acid in this example, and it will make ammonium chloride. You could either, once again, keep them together or you can break them apart, whichever way you want to do that. You could just write ammonium chloride on the right-hand side, whichever way you want to do. Since we are adding, just like all the other ice tables we talked about, we do need to do this in moles. So we're going to initially here, and again, we are starting with that guy. We are adding the acid in this case. So I'm going to make up my number of 4 moles. And as you know, right, since we are before the equivalence point, the moles of my HCl should be less than what I started with, right? So again, I'm going to make up my number of 2. Let's keep a nice whole numbers. This would be zeros. Change here would be -2, -2, +2, +2. Or you may just have one thing if you kept them together on the other side. That is going to get us here 2 moles of this guy, 0 of this guy, 2 moles of this guy, and really 2 moles of this guy. By the way, the Cl minus here is what type of salt? Cl minus came from HCl, which means it should be neutral, which means you really don't even have to worry about it, right? So if you did separate it, you might not even want to put numbers there, right? So we don't maybe use them incorrectly. So at this point, we do want to convert this back into molarity using our total volume like normal. And that means that I have really left over NH3 and NH4 plus. Are those things related to each other? They are. That is a weak base and its conjugate acid, also known as a buffer. Yeah. So much like the last one here, you will actually end up with a buffer, which means at this point you could go into the Henderson-Hasselbalch equation. Couple of things you do want to watch out for. You want to make sure, again, you get the base on top, you get the acid on the bottom, and probably in this titration, you will be given the KB value, not the KA value. So you want to make sure you use the pKa value in there. That's also where you can use the relationship that the pKa plus the pKb equals 14. So you can take the KB value, get the pKb, subtract 14, you'll have your pKa value. Or you can use KW and get the Ka and get the pKa, whichever way you want to do it. But you got to make sure that you have, again, the pKa value in there. So much like the last one, at this point in the titration curve, you will always end up in a buffer as you go from adding the first drop to before the equivalence point. And it will actually, in most cases, be pretty much a basic buffer almost all the way through. It might turn acidic towards the end, but it'll be pretty much basic for most of that run while it's sort of a real buffer at that point. So kind of similar again to the last titration, except it's more of a basic buffer, which you could still handle with the Henderson-Hasselbalch equation. Coming question? Yeah. Yeah, but you will not, that will not be the pH, that would be the pOH. Yeah. So you can use that one. Then you still have to subtract 14 at the end of it there to do that. All right, so let's take a look at number 3, which is the equivalence point here in this titration. So at this point, we're at the equivalence point. So we're going to have our HCl, our NH3, that's what we're adding or not adding. And that will give us our NH4 plus and our Cl minus here. We are once again going to do this in moles. So this is what we're adding. This is what we're starting with. So I'm going to use my 4 moles. And because we are at the equivalence point, we should have equal number of moles at this point. So we should have 4 moles of this guy and 0 of this guy. Change here going to be 4 because you can't choose wrong. Why am I ignoring Cl minus? Yeah, because why put numbers at this point? So again, we don't kind of mess it up. At the equivalence point, we're going to have 0 of this guy, 0 of this guy, and we'll have 4 moles of this guy, which once again, we will convert back into molarity by using the total volume. Now, looking at our ice table, we can see that we have NH4 plus left over. We already ruled out Cl minus. What about NH4 plus? Does it do anything? NH4 plus comes from NH3, which is a weak base, which means this will be a conjugate acid and will go through hydrolysis, right? Because it comes from a weak base. So much like the last one, at the equivalence point, you will need a second ice table, which is really a hydrolysis reaction between the salt and the water. And because it's going to act as an acid, it is going to send the H plus over to water. And the result of that is we will make NH3, which is where it comes from, and we will make H3O plus. Now, once again, without doing the calculation here, we should expect pH to be acidic because we have H3O plus. We also need to use a Ka value in this calculation. So much like the last one, we're going to take our equilibrium concentration here and basically put it into here as our initial. The rest of these will be zeros and X's. This obviously, as we just mentioned, should go into, not that, it should go into our Ka value, which is like B if you want to do it wrong. But let's go with Ka here. There we go. Ka value, which again is what we should have because we have hydronium ion. In this case, once again, we would solve for X. And once again, you probably will have to use the KW to get to the Ka value, as you most likely will have the Kb value given to you. In this case, though, we do see that X will equal the H plus concentration, which means you could go into your pH at that point to get there. So much like the last titration, when you reach the equivalence point in this type of titration, you will always end up with a salt that came from a weak base. And that means that that salt will always act as an acid and go through hydrolysis and always produce H3O+, which means you should always have an acidic equivalence point in this type of titration. So in a strong acid, strong base titration, you have an equivalence point that's neutral. In a weak acid, strong base titration, you have an equivalence point that's basic. And in a weak base, strong acid titration, you have an equivalence point that's acidic. So knowing where your equivalence point should be is helpful when you're doing titrations. Also could help you know that if that is your equivalence point and it's acidic, you probably are starting with a weak base or something like that. Any questions on that there? All right, to finish up this titration here, we're going to continue on to the fourth part here, which is past the equivalence point. And by the way, here we can see on the graph that is acidic right there at the equivalence point. So past the equivalence point, we once again will have our equation of NH3 plus some HCl, NH4 plus, and Cl minus. So again, we're going to do an ice table in moles. We're starting with our NH3. We are adding the acid. So we're going to take our 4 moles. And much like we've been talking about, since we are past the equivalence point, we should have more moles of the HCl in this case. So I will make up the number of 6. We'll go with 0. Change here again is going to make the base the limiting reagent at this point in the titration. So that's going to be -4, -4, and +4 moles. When we reach equilibrium here, we got 0, we got 2 moles, and we got 4 moles here. Once again, taking the total volume, I'm going to convert everybody back into molarity. And when we look at this titration at the end here, we have really 2 things left over. Both of those things are really a acid. Yeah. So as we saw at the equivalence point, that's a conjugate acid, and that is a strong acid. So much like in the other titration, the major contributor to the H+ in this case should be the strong acid. So we once again at this point in the titration, past the equivalence point, we'll ignore the contribution of the salt, because once again, really the HCl just needs to go for a swim and it will produce H+ really quickly, and that's all it has to do. So because that is a strong acid, that would obviously give us our H+ concentration, and then we go into our pH. And there it is. Yeah. So this type of titration is very similar to the last type of titration we talked about. It's just kind of going the opposite direction. So again, instead of going from acidic to basic pH, we're starting at a base and dropping down to an acid. Question on that one there. Question on titrations, big titration day talk. All right, what I'd like you to do is this. Would like you to work through this example at home, have it done, and we will kick off on Thursday going through all the parts of this. Yeah. So you could check. The goal would be for you to do it before you get here, so you could check to see if you did it correctly would be a good idea. Watching me do it is, you know, good, I suppose, but make sure you do it before you get here. All right. Any questions on any of that there? All right, we'll lay it up.